Hello everybody. This video we're going to be working out the period of a conical pendulum. So a conical pendulum is essentially you have your sort of fixed center and then a rope of some length, and then you have a mass tied to the end of the rope, and it is swinging. The motion is in 3D, so this traces out a cone shape. If I could, make it look like that. And so we want to find the period, right? Uh, for this mass to go around um, one revolution. So for now, I'm just going to solve symbolically. So I'm going to say the mass here is m, the length is l, the angle. So here we're given the angle with the vertical is 27 degrees, but I'll just call that theta. Um, like so. And what else? That is, yeah, so that's all the information we're given, and we're extrapolating the period. So we're also given that, we have gravitational acceleration, but um, we're just going to reserve that as g, and I'll just let it be 10 for now, 10 meters per second squared. But I'm not going to show any calculations. I'm just going to be solving symbolically. Um, so first we need to figure out the sort of the velocity, right? How fast is this mass going? Because that could tell us, how how quickly it goes one lap. And specifically, we want to know the uh, angular velocity, right? How many radians per second is it going? Because then we can just divide 2 pi by our speed, and that gives us t. So one thing we notice is that if this mass is traveling in a perfect circle, then it is going under uniform circular motion, which basically means that the acceleration towards the center is equal to its angular speed times the radius. The radius here we can find via trigonometry is L sine theta. So this is omega squared times L sine of theta. But how can we actually find this acceleration? Well, we know that the rope is pulling on this mass with some tension force, which I know we have period here. I'll just call this capital T because I tried to sort of give the period these little hooks here. So I'll just have a normal T here. So we have some tension force, right, pointing in this direction. And so again, we can apply trigonometry because so we have T, but then it has a horizontal and vertical component, but with the same angle theta. So the horizontal component is equal to ma, where this acceleration. And the horizontal component is just t sine theta. So t sine theta is equal to ma, right? Um, and so I'll just substitute a. So m omega squared L sine theta. So here we see that the sine theta cancels, and we have an expression for our tension. So next we can figure out um, the vertical component of tension, which is t cosine of theta. And that's mw, or m omega squared L times cosine of theta. And what is this equal to? Well, if we have a mass, let's just draw a free body diagram for our mass. It has a vertical tension acting on it, so T vertical, I'll call it. And it also has the weight, or it has its own weight, which is just mg. And since this mass isn't traveling in the z direction, if we call this xy plane, it isn't traveling in the z direction, so these forces must be equal to each other. So in other words, m omega squared L cosine theta, which is the vertical component of tension, is equal to m times g. And here our mass cancels out. And here we can see that we now have all things that we know. We have g, L, and theta, and what we want is omega. So here we can solve just for omega, and we get omega is the square root of g over L cosine theta. And so now our period, which was 2 pi over omega, is just 2 pi times the square root of g over, or sorry. So we take the reciprocal, so L cosine theta over g. And this will be the time it takes in seconds for the mass to revolve once around this conical path. Thank you for watching this video. I hope you enjoyed it, and I'll see you in my other videos.